Good morning. Welcome back. We continue on with Chapter 11. This is going to discuss how we set up an experiment when we're conducting an experiment built between multiple different categories, and how we do a test of means between those different categories. Okay, so far we have done hypothesis tests for one sample mean. We've obviously done it for variance and proportions, right? But I'm just going to talk about the means for now. So we've done it for one sample mean and two sample means. Okay, so now we'll talk about hypothesis test between multiple means. Okay, and when I mean multiple, I mean greater than or equal to 3. Greater than or equal to 3 different samples. Okay, because for 1 we've already done a hypothesis test, for 2 we've done the same, so anything 3 or more can be handled by this setup. And we cover that through the topic of ANOVA, okay? Analysis of variance. Okay, so we'll first define some terminology that we need to do, that we need to understand in order for you to do a ANOVA test. Okay, and we're going to learn only a one-way ANOVA, and we'll define what that means. Okay, so far we've only considered collecting and comparing either a single or 2 different data sets, right? And we've done that using independent assumption or dependent assumption. And when it was dependent, we did a paired t-test. When it was independent, we compared 2-sample t or pooled t, or we did single sample tests. Okay, well, what if we wanted to compare more than just 2? In that case, we perform an experiment, okay, where we systematically study 1 or more different factors, right, important things that affect your study, and see how that differs between different groups underneath that factor. Okay, so in an experiment, you have strict control over what contributes to the outcome. Okay, and there are multiple groups for each factor. For example, if you're testing on medical drugs, right, the experiment has a placebo group and a group that actually administers the drug. So those 2 are the different levels, the placebo and the drug, right? And the factor is the experiment that you're conducting, the main overarching topic. Okay, and the responses is how you respond to the drug. Okay. And we'll look at an example for that as well as we move forward. Now, the experimental units is the individuals that go through the process of running an experiment on them, right? If it's a medical experiment, that would be you, the subject, and that would be the experimental units. And if the treatment is being repeated multiple times over and over, those replications are the responses. And the way we set this up, right, the entire experiment is called design of experiments, and in this case it's a designed experiment where we want to test between different groups. Okay. If it was completely random, right, each different response or sample, i.e. you, the subject, is going to be randomly assigned to the different groups. For example, there's 3 different experimental units assigned to 5 different treatments. You just randomly assign them, or 5 different groups. Okay. Now, once the experimental units or the samples are assigned to each of those levels, you obtain the responses, or a sample of values. And then the goal is to identify if there's a difference between the different groups. And one of the assumptions is that the data that's collected is independent from each other. Okay, because if it was randomly assigned, then they have to be independent from each other. Okay, so based on that setup of an experiment, we perform a hypothesis test on the different means. Okay, and we want to study the effect of those different groups, right? P different groups. We call them treatments, or we call them levels or groups. Typically use the word levels or treatments. Okay, so we want to see for each treatment if the mean and standard deviation helps us understand that there is a difference between those treatments or levels or groups. And we do that through one-way ANOVA. Okay. It fits it to a model and then compares the effects of those different groups on the response. And it does a hypothesis test on mu1, mu2, mu3, mu4, depending on how many different groups there are, levels, that many different mu's. Okay. And then we do a one-way analysis of variance, ANOVA. That's why it's called ANOVA. Okay, a little bit of terminology. We're going to denote Ni as the sample size for treatment I, okay, and N as total sample size. Okay, where N equals to the summation of Ni over I. Okay, so when you sum up all the sample sizes of the individual treatments or levels, then you get the total sample size. Okay, and Xij is the value that goes into the jth value that goes into the treatment I. Okay, and X bar I is the average of the sample in the Ni different values in treatment I. And Si is the standard deviation of the sample of the Ni values in treatment I. Okay. To visualize this, think about, let's say you want to find out if there is a difference between total cap sales in 4 different locations, and you want to find out which location sells more. Okay, so you have location A, location B, location C, and location D. Okay, and you have a bunch of different sales all listed here. Okay, these are not zeros, I'm just not writing the number. These are all the different sales that are listed over the different months. Let's say last year. Okay, in that case, your levels or treatments are the different locations. Okay, so this is levels or treatments, 4 of them, A, B, C, D, and location is the factor, right? Ideally, I would have written location as the main heading, and then A, B, C, and D were the levels or treatments. Okay, so location is the factor. So when you're trying to find out what is the factor and what is the levels, think of the big picture, the big topic that we're talking about as the factor, in this case location, and the different options that you have for the factor is levels or treatment. Okay, levels and treatment are the same thing. So there's 4 different levels in this example and 1 factor. We're only going to cover 1 factor ANOVA. We're not going to do 2 factors. And there is 2 factors, but in this course, we're only going to cover 1 factor ANOVA. Okay, and each of these different values are responses. They're the sample points. You can call them samples or responses. When they talk about responses, individual values is what they're talking about. Okay. So why do we do it? The goal is to find out if the difference in means actually means that the samples are different from each other. That's what ANOVA tells us. Okay, so look at picture A and picture B. Picture A shows 3 different data sets. These are the box plots. And the difference in mean is about that much between the 2 different groups. And that's the same difference as we have in picture B. Same difference in means. Okay, but the spread inside the data sets here are much larger than the spread inside the data sets here. So A has much larger variation within the data sets. A has larger variations within data sets than B. Okay, so the difference in means for B, even though they're the same amount as difference in means for A, is much more pronounced. Okay, it's much more significant than the difference in means in A, because A varies so much. You can see within the data sets that this difference between the means might just be random chance. okay, random luck. But this difference, even though it's the same size as this difference, right, A and B, the same difference in means, in B it's much more significant because to begin with, the data sets in B don't vary that much. And that's what we are trying to measure mathematically. This is just a picture version of what we're trying to do. And we do that using the F-test, right? Remember, we talked about the F-test for what? Comparing two variances. Right, we talked about the F-test for comparing two variances. In fact, you're going to see that we are going to compare two different variances, but the test will be on means. So here is a little bit confusing and non-intuitive part. We're going to do a test on the means, the averages, but we're going to get to the solution by comparing variances. Okay? And it's only if the overall F-test showed that there is a difference between the means, then we're going to do something called a Tukey comparison test, pairwise test. Okay? Okay. Now, the way ANOVA does that is it compares the different means by also looking at the spread of these different distributions. Right? We talked about the variance. Okay, and it fits it to a model where each individual data point, xij, can be represented by the population mean, mu, and some error, eij. Okay, and that error term we call residuals. And we're going to use these definitions in the next few chapters as well, in chapter regression and the multiple regression. Yeah, every time we usually have a predictive model such as this, there will be residuals. Okay, and we assume that these residuals are normally distributed with a mean of 0 and a constant standard deviation sigma. Okay, so those are going to be one of the assumptions that we test for. Okay, and finally then we do an F-test where the hypothesis for ANOVA is that mu1 equals to mu2 equals to mu3 equals to mu I or P, whatever you want to call it. Let's call it P because we've used that before. Mu1, mu2, all the way to P of them. If there's P different values we're testing for, P different data sets that we're testing from, okay, and the alternate hypothesis is going to be written in words, and it's going to say not all of the mu i's are equal, or at least one mu I is different than the rest. Right? They don't all have to be not equal to each other. So HA or H1, whatever you want to call it, if you write mu1 not equals to mu2, not equals to mu3, not equals to all the way to mu p, this is wrong, right? Because this says all of them have to be not equal to each other. That's wrong. The null hypothesis is that they're all equal to each other, and the alternate is that at least only one of them, it can be only one of them, it can be more, at least one of them has to be different than the rest. That will break your null hypothesis. Okay, and we compute F by comparing the spread of data, sum of squares, between the groups G and the sum of squares within the group, which is the errors part. Okay, we'll look at that through the ANOVA table, how to compute that. Once we find f-stat, we can then find p-value and make your conclusion. Right? Find the f-stat, find p-value, make your conclusion just like you did before. F distribution has the degrees of freedom of the numerator and the degrees of freedom of the denominator. So what is F really measuring? So it measures the variation between sample means, right? If you want to change some of these words, think of this as between, right? Compares sample means between the sample means, and the denominator is variation within each sample. Okay, so within is the spread inside a data set. So this is, let's say, 3 different data sets, right? 3 different samples. Not sample as in each individual point, but 3 different groups of data. Okay, so with 3 different samples, this one has a much larger spread within, inside each of the data sets compared to this one, right? But the variation between the means, which is, for a box plot, right, this is the median, or mean can be somewhere near that. Well, that gap is the same as the gap between those lines, right? So if we keep the numerator the same, so the variation between the means is the same, but variation within the groups differ. So in this case, this is higher, larger, so the denominator is going to be larger in this case in A than in B, right? And because the denominator is larger in A, the F value is going to be small, right? Because it's defined as that. And in this case, the F value is going to be large. When there's a large F value, you're going to most likely get a small P value, and a small P value will mean reject null hypothesis. So we have significant results. Okay, so the assumptions for doing these tests is constant variance. We have to assume that the P different populations that we have of the treatments all have the same variance. Not zero variance, but the same variance. And we can check that through residuals that have to be distributed normally with a mean of 0 and a standard deviation sigma. That's what it shows, that all the different residuals from all the different treatments or levels have to have a constant variance, right? Sigma, or sigma squared, which is variance. And we have to assume that the data came from a normally distributed population. So we're going to have to check for normality. Again, we do that through residuals. There's a plot for this one, and there's another plot for this one. And similarly, there's also going to be another plot to check that they are independent. Okay, so let's put some numbers in our context. Whenever you run ANOVA, and you're going to run this in Minitab, always, right? There won't be any hand calculation. The only hand calculation that you may have is to understand this table. This is the Minitab output. Okay, this table is what Minitab gives back to you. Okay, and to understand it, you have to be able to get each of the values back, and you have to know the connections between these different values. Okay, these are questions that will be on the test. Okay, so first off, the p-value, most important thing, right? It helps us do one thing. p-value less than alpha, reject. P-value greater than alpha, fail to reject. Right? Our null hypothesis, mu1 equals to mu2 all the way to mu, let's say p, versus our alternate hypothesis, mu I is at least different in one level. Okay, you have to write that one in words. Right, so if p-value is less than alpha, it proves to us that at least one of the means is different in the different groups. So there is a difference between the different levels. Okay, and then it is also very important to be able to derive these values. Now, I'm not going to expect you to hand calculate each of the different standard deviations in the levels I and plug in these values. Okay, so typically when we give these questions, in the first column, or the column that has sum of squares, SS, okay, 2 out of these 3 values will be given. Okay, 2 out of these 3 values will be given to you. The third one you can find out easily because this number plus this number gives you the total. Okay, total is just these two, the rows summed up gives you the total. Okay, the sum of squares between the groups is nothing but a measure of, as you can see, the average in level I, or you can think about them as different columns, right? So the average of column I minus the overall average, this is the average of all the data, okay, multiplied by the sample sizes. So what it does is it measures the differences between the means, like we talked about before, right? And this measures the variances within the different samples. So SI is the standard deviation, or SI squared is the variance of level I, or column I, right? And then we're going to scale it by the sample size in that level. Okay, so this is variation within. Okay, so this is variation between, this is variation within. When you sum them up, you get total variations, SST. Okay, now to understand degrees of freedom. This first one, when you're talking about between the groups, when this is about the treatments, the levels, this is basically the number of levels minus 1. Number of levels minus 1. Okay, so that's why there is I different levels in this example. If you want to call it P, you can. We've been using P so far, so P different levels. Okay, that's different than p-value. This is p-value. Okay, so if there's p different levels, this would be p minus 1. So if there's, let's say, that cap design example that we talked about, right, there's 4 different locations, so this would be 3. Okay, now it's easier to possibly find the degrees of freedom of the total. This is sample size minus 1. Total sample size. Okay, so sample size is n. Let's say you collected 100 data points. 20 in location A, 30 in location B, 20 in location C, and 30 in location D. Well, then this would be 99. Okay, and this then is just the gap between these two numbers, because this number plus this number gives you the total. So n minus 1 minus p minus 1 is just n minus p. So if you had 100 data points that you took and you had 4 different locations, right, the treatments, then this would be 96. Okay, so these degrees of freedom you derive from the situation or the data set or the question you're asking. Once you find the degrees of freedom, then you take the sum of squares of the group divided by the degrees of freedom, and that gives you mean squared of the group. So MSG. This is mean squared differences between. Right? One way to learn this is to know that we're talking about here a mean. Right? A mean. A mean is nothing but a sum divided by size. Right? Degrees of freedom is a measure of size. Right? How do we find an average? We sum things up and divide it by the number or the size. Right? So the same thing here. We're going to sum it all up, all the differences, and then divide by the degrees of freedom to find the mean square variances. And you're going to do the same thing for the errors to find mean squared error. Okay, sum of squares of the error divided by degrees of freedom gives you mean squared error. And then you're going to divide the top, the mean squared between, divided by mean squared within. Why do you do that? Well, remember, how do we find F value, F stat? This is the F stat value, okay? Why is it MSG over MSE? Go back to how we defined it here. We said it was the variation between the means divided by variation within the groups. So going back to here, this is the variation between the means, right? Remember we said between the means, and this is the variation within the groups. So we divide the top by the bottom to find F statistic. Once you find F stat, based on that you find the p-value. Okay, and when you're going into Minitab to find that p-value from this table, right, it's going to ask for the degrees of freedom. So you put the corresponding degrees of freedom. So the degrees of freedom for MSG, if MSG is in the numerator like it is, then you put the degrees of freedom in the numerator and this degrees of freedom in the denominator because MSE is in the denominator. Okay? Alright, so let's look at an example. You're trying to look at a study if the effect of a model's eye color has any changes on the response of an advertisement. Okay, and you study 4 different colors: blue, brown, down, which is gray, and green. Okay, and you collect sample sizes. As you can see, for ANOVA, sample sizes don't have to be the same. You find different sample sizes in each of those different treatments. You have the means for those different samples, and you have the standard deviation. Okay. So when you compare them next to each other, well, it seems like there really isn't much of a difference between them. Right? They overlap together. I wouldn't expect there to be any difference between the means of them, just visually looking at it. Right? So let's run some numbers to test for that. Well, first we have to check for normality, right? Assumption normality, and we do a normal quantile plot. And it looks fairly normally distributed. Okay, normally distributed, so this is good. And assuming the other assumptions hold, Minitab then gives us back this output. This is called that one-way ANOVA output. Right? It's the same table that we just went through. Right, so if sum of squares is given to you, you can see that when you add these two things up, you get the total. Okay, and remember there's 4 different colors, right? 4 colors. There were the treatments, therefore the degrees of freedom for the group is 3, and they had collected a total of 222 samples. When you add up all these numbers, n, you get 222. Okay, so therefore this is 221, and the error degrees of freedom is 218. All right. And when you divide 24.42, the sum of squares, by 3, you get 8.14. And when you divide 613.14 by 218, you get 2.81. Okay, and MS group, MSG, divided by MSE is the F value. So 8.14 divided by 2.81 is 2.89. Now you go to Minitab, plug in 2.89 to find out that the p-value is 0.04. Right? So surprisingly, even though I thought originally that there wasn't a difference, turns out the number tells us, because p-value is less than alpha, we reject the null hypothesis that they are all the same. And so we have evidence that at 5% alpha, there is difference between the groups. They do not all have the same mean. All right, and if you were to do this using tables, then once you find the F value, you go to the table, look it up using the degrees of freedom, and you find the p-value. Another example. You know that yogurt can be made using 3 distinct commercial preparation methods: traditional, ultrafiltration, and reverse osmosis. You want to study the effects of these methods on taste and experiment if there is a difference between tastes of those 3 methods. So you select 10 different, 9 different trained experts. They taste the yogurt for each of the 3 different methods. Okay. So what is our degrees of freedom between the groups? Well, what are we comparing? We're trying to see if there's a difference between traditional, ultrafiltration, and reverse osmosis, the 3 different methods. Right, so those are our treatments. So therefore, this is going to be 2, right? And we have 9 different samples. So this is going to be 8, right? 9 minus 1, and therefore this is going to be 6. Or you can also think about it as 9, which is n, minus 3, which is the number of levels we have, 6. And then 17.3, the sum of squares between the groups divided by the size, gives you mean squared, and 4.6 divided by 6 gives you 0.67, and 8.65 divided by 0.767 gives you 11.283. Then you take your 11.283. If you're using the table, you look at the degrees of freedom in the numerator in the row, first row, and degrees of freedom in the denominator in the column, and you try to find out the F value from the table. Or else you use Minitab, and Minitab gives you the p-value. Okay? And the way we compute the F value, again, to remind you, is MSG over MSE, right? That's nothing but measuring the spread between the means, comparing it to the spread that occurs within the groups. All right, so let's run through a full-blown example. Okay, we're going to run through a full example for ANOVA. Okay, so it says, if a supermarket product is frequently offered at a reduced price, do customers expect the price of the product to be lower in the future? This question was examined by researchers in a study conducted on students enrolled in an introductory management course at a large Midwestern university. For 10 weeks, 160 subjects read weekly ads for the same product. Students were randomly assigned to read 1, 3, 5, or 7 different ads featuring price promotions during the week. They were then asked to estimate what the product price would be following weeks. the table 14.2 gives us the data set. Now for you, I have uploaded this file price promo onto the module section that you're going through. Okay, you'll be able to download that file straight from Canvas and open it up right now using Minitab. Okay, and try to work through this as we go along together. Okay. So it wants us to test. It says make a normal quantile plot for the data and show that the 4 treatments are normally distributed. In fact, we won't have to do that. We can show all 4 of them are normally distributed through one plot, and we'll look at that. Okay, so instead of individual normal quantile plot, we will use the plot on residuals. That will test for all of them in one go. Okay. Then it says summarize the data. Again, don't worry about that so much. We want to go through the example and see how to do an ANOVA. Really, so part D is the most important. Okay, and it says check if the assumption of equal standard deviations or variances is reasonable. Again, we will do that through a residual plot. Just like here, but a different plot. And it says carry out a one-way ANOVA, state the hypothesis, find out the test statistic, its degrees of freedom, p-value, and summarize the conclusion. So let's have a look at the data. So in the first column, that's just a sample number, so you can almost delete that. It doesn't really help us with anything. We have the numbers right there. In the second column, it says how many promotions were given out. So these are your levels. Okay, so this column are your levels, or if you like to call it treatments, then they're the treatments. Oh, excuse me. They're the treatments. Okay, then there's another column of data discount, which we don't have to pay attention to in this question. It's just another category. And then the important column of price, which are your responses. Right, so the question is, does your response change, does the price you pay change depending on the number of promotions that you were given? That's the question. If you scroll down, you'll see there's more data sets. This is only 1 and 3. There's 5 and 7 as the other promotions. Okay, so starting off, we go to Minitab. So click on Stats. Okay, and then go to Analysis of Variance, or ANOVA. Okay, and then go to One-Way ANOVA. Okay, the first one-way. Once you click it, something like this pops up, this dialog box. Okay. Click on the arrow, the drop-down arrow, and then you have 2 choices. Responses are in one column for all the factors, or responses are in separate column for each of the different factor levels. Right, so are they all in one column for all the different factor levels, or is it in different columns? What do you think for our data set? Go back to that setup. These are the responses. Are they in different columns based on the different promotions? No, right? They're all in one column, all the prices. So responses are in one column. That's what you click. Then you have to put in what's the response and what's the factor, i.e. the levels, right? So price is our response, right? Price is a response, And these are the levels, 1, 3, 5, and 7. Well, what's the factor for those levels? Promotion. Right, so factors is promotion. And response is price. So it's very important that you identify those two, what they mean. Okay, then after that, click on comparisons. Okay, when you click on comparison, this pops up. This is where you have to select Tukey, none of the others, but Tukey. We're going to do Tukey pairwise comparisons. Okay, all of these other groups, everything else defaulted will be fine. Just leave it as it is. The checks where they already show up. Don't change the error rate. You click on Tukey. Okay, then after, click on graphs. Once you click OK here, go back to the main dialog box and then click on graphs. And this pops up. The interval plot will be default checked. The residual plots will not be checked. Change that to 4 and 1. Okay, so click on 4 and 1. If it says 3 and 1, then click on 3 and 1. If it says 4 and 1, then click on 4 and 1. Okay, if the data is separated in different columns, you will only get an option for 3 and 1. If it's all in one column, you get the option for 4 and 1. Okay, then click OK. And then click OK. Okay, so click OK and then click finally OK to run ANOVA. The first plot that you get out looks like this. It's the interval plot. Okay, this plot is for visual interpretation. Okay, it's only for visual interpretation. So what does this show? This shows the interval, 95% confidence interval on the mean. So this is the mean right in the middle. Okay. And then it's the 95% confidence interval. So this shows some overlap between them, right? This one and this one overlaps a little bit, right? And this one and this one overlaps a little bit. But there is no overlap between these two categories. So there is a overlap in this group and an overlap in this group. All right, so we can tell that the price of treatment promotion 1 and price of treatment promotion 3 are similar to each other. They're not different. And price of 5 and 7 are also similar to each other. They're not different. But there is a difference between all 4 categories, and that difference lies between the 2 different groups where 1 and 3 is similar, 5 and 7 is similar, but there's a difference between 3 and 5, 1 and 5, and 3 and 7, and 1 and 7. All right, so that's what we expect. So let's actually look at the numbers to confirm that. Well, first off, you have to make sure your assumptions hold. And this is where you check your assumptions, right? Check all assumptions using residual plots. And these are your residual plots. Okay, so first thing, you're checking for normal distribution. So this is a normal probability plot, also called a quantile plot. If the dots are along the line, like we talked about before, it is normally distributed. So this looks good. All right, so we have normality. Then we have to check for constant variance, right, or equal variance. We do that using residual versus Fitts plot. Okay, so this is called the residual versus Fitts plot. Okay, and you see that the middle line is 0, and that the data looks somewhat uniform, right, with the spreads. Right, this is the spread of the data. Okay, so if they are within some kind of bandwidth, right, for this plot, if they are within some kind of bandwidth and there is no pattern happening, then that's good. Okay, so that will show constant variance or equal variance. Okay, and to describe this, you want to use words such as residuals are randomly and uniformly distributed around 0 for this plot. Okay, that will show equal variance, right? Because if it's equal variance, that means the spread is the same between the levels. Well, then they're all going to be within a bandwidth. And to describe that, you say, well, they're randomly, there's no pattern, and uniformly within a bandwidth distributed around 0. That shows equal variance. Okay, what you're looking out for are residual plots that looks like data increasing in this kind of pattern, or data decreasing in this kind of pattern, or if there is some kind of pattern going up and down or down and up. All those kind of patterns will show you have some issues in the data. Okay, anything significantly patterned as that will cause problems, and that will break your equal variance assumption. Okay, so you want to make sure it looks something like this for ANOVA. If there's more than 4, then you will have another category, 5 or 6, and so on. You want something to be sort of along a bandwidth to assume equal variance. Okay, and then the third one here is independence. Okay, and for that you want to check for residuals are randomly distributed. Okay, again, you're trying to make sure there is no pattern happening as that, or increasing or decreasing or so on. All right, so it's very important to check these 3 assumptions and know that this is normality. This checks for normality. This checks for constant variance or equal variance, the versus Fitts plot, and residual versus order plot checks for independence, right? Order. If there is no pattern inside your order, well, then they're independent. Each data point is independent from each other. Okay, well, now that your assumptions are good, we then look at ANOVA. This is what the output looks like from Minitab. Okay, So starting from the top, it says what our null hypothesis is. All the means are equal, right? Which in mathematical terms means mu1 equals to mu2 equals to so on all the way to mu, how many are there? 4. So mu1 equals to mu2 equals to, I can even write it out, mu3 equals to mu4. And h1 is that at least one mu I is different. All right, tells you alpha of 0.05, tells you that the factor is promotions, and there is 4 different levels, and those levels are 1, 3, 5, and 7. And then gives you the ANOVA table output. Tells you degrees of freedom is 3. Well, that makes sense because it's the number of levels minus 1. Tells you the sum of squares for the promotion, which is between the means, and then error, which is within the groups, right? Tells you MS values and tells you F value. 2.7 divided by 0.1 is about 25.65. And based on that, you find a p-value. So what's the most important thing here? P-value. Says that p-value is less than alpha, right? Therefore, reject H0, accept H1, at least one of the mu I is different. Okay? It's only when you reject H0, you look at Tukey, the pairwise comparisons. Okay, because this just told you that at least one of the mu I is different. But that doesn't really solve the entire problem. We want to find out which one is different, and which one is more, and which one is less. Okay, so only when you have proved that at least one of them is different, then move on, scroll down to the next part. And if you scroll down, then you look at all of this output, and it has the Tukey pairwise comparisons. Okay, and it provides this really nice, concise grouping information. It says means that do not share a letter are significantly different. So this shows letter A being shared between promotion groups 1 and 3, and letter B being shared between promotion groups 5 and 7. This is exactly what you saw in the original interval plot, right? You saw 1 and 3 being similar, 5 and 7 being similar, but there's being a difference between them. So Tukey confirms it. Great. Tells you that average, so mu of 1, right, is equal to mu of 3. They are the same. Even though there's a difference in the numbers, it's not big enough for them to be different. Okay, but that is bigger than mu1 is equal to mu3, but that's bigger than mu5, which is equal to mu7. So this group is similar and that group is similar, but this group is bigger than that group, right, based on the means. That's a sizable finding. So if you now had the option to find out how many promotional activities that you would send, right? You know that 1 and 3 does far better than 5 and 7, and if it costs you more money to send 3 compared to 1, well, then just send 1 because there is no difference between them. All right? And then the final graph, which does the pairwise comparisons. So while you saw that the things are similar, the groupings are similar and so on, this exactly paints out the picture if they are same or not. And it says if an interval does not contain 0, and you can see 0 is in the x-axis, the corresponding means are significantly different. Okay, so right away you know 7 and 5 has 0 in it, and 3 and 1 has 0 in it. So these guys are similar. All right, and 5 and 1, 7 and 1, 5 and 3, and 7 and 3, they don't have 0 in their pairwise differences. Okay, this is a difference of means plot. All right, so I want you to logically understand what that means. This confidence interval is on the difference in means. So if 0 is in the confidence interval for the difference in means, that means there may not be a difference between the two means. If 0 is outside it, that means there is a significant difference in the means. Okay, so in that case, these 4 shows they are different. Okay, so 5 and 1 is different from 7 and 1, which is different from 5 and 3, which is different from 7 and 3. These two comparisons are different from each other. These two comparisons are different from each other. Same here and same there. But these two are similar, and these two are similar. All right, so to summarize, right, for ANOVA, first step you should do is state hypothesis. Next step, visually interpret interval plot. Next step, check assumptions, okay, and make note if any assumption fails. Then run ANOVA, right? Check p-value. If less than alpha, reject H0. If greater than alpha, fail to reject. H0. For number 5, if you reject H0 in step 4, okay, if you fail to reject, you stop right there. Test is inconclusive, you're done. But if you reject H0 in step 4, look at Tukey pairwise comparisons. Okay. 6, make conclusions on pairwise differences. That's ANOVA. All right. I want you to practice with that data set I uploaded on the promotions. See if you can do the same thing on the discounts, right? There's 4 different discount levels. Okay, so practice running ANOVA on that price promo example, but using discounts as factor. State what the levels are going to be. Okay, I think there's 4 of them. State what they are, set up the hypothesis, visually interpret, check your assumptions, run the ANOVA. If you get a significant result, look at the Tukey comparisons and make conclusions. All right, that brings an end to this chapter. Again, make sure you're following along. There should be a new homework up about this chapter and a few topics in the previous chapters. Make sure you complete it between now and the due dates. Okay, again, if you have any questions, contact me at aroy@bgsu.edu. Thanks.